Imagine if you have a special box called neural network. Inside the box, there are lots of tiny computers which will help it learn how to do things. So, tiny computers need something called activation function, right? So that's what tell them what to do. So activation functions are really special instructions that say if this happen, do this. There are a lot of different types of activation functions, and we are going to learn about them. So sigmoid, then ReLU, Leaky ReLU are some of those. Then those functions are all to say you that the slope of this function is like special number that shows us how fast they grow. So sigmoid function will be looking like something like this, right? Where this is A and this is Z, and G of C will be 1 upon 1 plus E of negative Z. So G of GZ will be G of Z equals to slope of G of X at Z, which means we can write it as 1 upon 1 plus E of minus C, 1 minus 1 upon 1 plus E raised to negative Z. And that's what it means. Like we can write that as G of C, 1 minus G of C, and that will be Z equals to G of C x1 G upon G by C, G of C equals to roughly 1 minus 1, which roughly equals to 0, right? So that's the basic thing for sigmoid function. And what happens after that is Z going to be minus 10, then this is going to be almost 0, this is going to be 0, into 1 minus 0 is going to be equal to 0 approximately. And we're going to have this thing, then we're going to have d by dc of dc 1 by z, 1 upon 1 by z will equal to 1 by 4, right? So g dash c is equal to 1 by z, 1 minus 1 by z equals to 1 by 4, and then g dash c is going to be equals to 3 by dc g of z, which will be a 1 minus a into 1 minus a, and where a is g of c equals to 1 upon 1 plus e of negative c. So that's our sigmoid function, right? So we're going to look about tan h function. So there are a lot of different things. So sigmoid function, the special is a special instruction that which says if you see something big, make yourself a little bit bigger. The slope of this function is like a math problem that shows how fast it grows. So we can solve that problem. So the formula for that is just what we derived right now. So as we can go through and look through. So this means if you see something big, your value will get smaller and bigger. But if you see something small, your value will get bigger and bigger. Let's try some examples. So if z's were really large, like 10, the slope is close to 0. Like you can see, imagine from this graph. If z is really small, like negative 10, the slope is also equals to close to 0. But if z is 0, then slope is half of the 1/4, which is a bit tricky. Now let's move to the tan h function, right? So let's go through that. I think writing that function over here might be a good idea. Let's go to tan h function. So tan h function looks like something like this, right? Now we're going to have tan h. We can write that as c equals to e raised to c minus e minus c. This will be looking like g of gc, g of c equals to slope of g of c at c equals to 1 minus tan c squared. And when c equals to tan h is going to equal to be 1. Now g of c is going to be equal to 0, and tan of c is going to be almost equal to 1. Then g dash of c is going to almost equal to 0. Then c is going to be 0. Then tan h of c is going to be 0, and c equals to 0. Then g dash of c equals to 1. Now we're going to talk what that means. So this instruction says if you see something big, make it smaller, right? So this is the other function where math problem is which math problem is which shows how fast the function grows, and guess what, we can solve the math problem too. So the formula for that is what we wrote right now. So let's try some examples now. So if z is really large, like 10, then slope will be close to 0. If z is really small, like negative 10, then slope will be 0. But z is at 0, then slope is going to be 1. So that's about tan h. Now let's talk about ReLU. So ReLU and leaky ReLU. So let's go with the ReLU. So this is our ReLU function. This is a, this is c, and let's get math. this is if z is equals to, like, z is lesser than 0, this is if z is greater than 0, and this is if z is equals to 0, right? Okay, so if we implement this in software, it might be not completely right, so z might be equal to 0.00000 something, and yeah, reloop. So the instruction will be saying, like, if you see something lesser than 0, then do nothing. So this thing is do nothing, and that's all it is. So slope of these functions is like spectral number, which shows how fast they grow. The formula of a reloop function is just these things which we are going to write now. So the formula is g of gz equals to 0 if z is less than 0, then 1 if z is greater than 0. This means if you see something less than 0, your value will stay the same, but if you see something more than 0, your value will get bigger. Let's try some examples. If z is really small or negative, let's say 0.5, then our value will be 0. If z is positive, let's say 2, then slope is 1. The leaky reloop function is similar to reloop function, but it has simple tricks. So this thing will be little bit going to this, like, that's why we say it has leaky reloop. So if you see something lesser than 0, then your value might get little bigger. The formula of leaky reloop will be g of gz equals to 0.01 if z is less than 0, and 1 if z is greater than 0. To sum it up, actuation functions are like special instructions that tell our tiny computers what to do, and we need to understand how they grow and change. So we can use math problem to how to use Java. So that's all for this video. Let's see you guys in the next one, and keep hustling.